So this video is 6.2 on volumes using the cylindrical shell method. Just a quick, though, recap of the volumes by cross-section. This is the one we just did in the previous video if you're going in order. And this is what I didn't have up originally. So this is kind of like that generic curve of some sort. And then you do a cross section of it. Like you literally just go perpendicular to the axis of whatever that is. And you get this cross section, right? You get this piece in here. And so this is how it's set up and how you would end up driving it. And that's the cross section you're looking at. And so you're adding up those pieces. So that's going to be your delta x, right? So when you look at the difference there, there's your delta x. Okay, so if you know this area, then you do the delta x, and then you add up those pieces all the way across. You do that one, you do that one, and it's going to change, of course, as x changes. And you could put it vertical and change as y changes. That's kind of how we did above. Okay. So let's now look at volumes using cylindrical shells. Now I looked up, I don't always do this, but I know this is a very typical method. Everybody does this. So I looked up and Googled, actually I'm not using Google anymore, but I looked up and did a search engine on this method, and there's all kinds of videos. So if what I do you don't like or want to see something different, there's a whole bunch of different methods for cylindrical shells, washers, and all that to see a different perspective on it. It almost seems a little silly that I'm doing these, but I think it's better that I do. Okay, and I did not see the actual derivation. I didn't look through a lot of them. I just look at the basics, and they don't show the derivation usually. And that's one thing I want to get across is this stuff doesn't just pop out of thin air like it just works. Like you have to use a Riemann sum concept and do it like that. Okay, so let's take a look at this this graph here. Y equals, and then it's right there. I just drawing a little bigger. It's x squared minus x cubed. So it's just a polynomial. So the polynomial does this sort of thing. It's a cubic, opens, reverse order, right? It goes like that. So I actually, not really erased, I really couldn't erase it, but on the math program I have, I copied it over. And let's suppose you want to take then this region. Let's see, let's take this region here. You want to do this region and revolve that about the y-axis. So this is what I want to look at. And so if you were to use, let's see, if you were to try to use shells, then we'd be going across this way. Oops. Then we'd be going across this way. Okay, so if these were, did I say shells? Washers. If these were washers, we'd be going like that. But then you have an outside and an inside. But now this is delta y. So it would be the case above where you have a delta y. And so you'd have outside, this would be like your f of x. And this would be your g of x. Oops, not x. It would be y, huh? This would be your g of y. And it's the f of y. G of y. That's what you'd end up having. So this allows us to do another way of looking at it and using what are called cylindrical shells. Excuse me. So let's take a look at that. I'm going to erase everything. So we're not going to do that. We're going to do, oops, I actually wanted that one. So we're going to take this region, and we want to revolve around the y-axis. Okay. So take that, make it a little nicer there. And we're going to go this way. So now let's instead put in a, and you know what, I'm going to erase all that because it looked too much. Okay, we'll just do it like that. So we're going to take a vertical little rectangle like this, and we're going to revolve that. Okay, so we're going to take this, and you can picture that. So there, that's a delta x. And then we're going to revolve that around the y-axis. So this is y, right? And this is x. And so it's going to be, and let me try to do this so I can, it doesn't want me to do that, so I can draw better. So we're going to go this way, like that. And so what you end up with is this shell. It's, again, kind of hard to draw. Okay, so you end up with this shell, and I'll draw it below, make it look a little better. So what you get, and you can see then, oops, sorry, as you add that up across, you get these concentric shells, and that creates the volume. Picture doesn't look good, but you get the idea. And so what you end up having then are these, that seems to never work for me. Okay, that's better. Okay, I know, too much silence. I'm trying to move that, but it won't move. All right, so duplicate. There we go. You get these things. So you get these, they're like cylinders, but we call them shells because they're like one inside the other, like this. And then that goes down. So what you want to look at then is this. You have, when you, let's find the volume of that. So let me write some of this down. So find the volume of the shell. And so what most videos I was looking at anyway show you is basically they go right to the formula. They'll say outside altitude is the difference, and then it's just 2 pi times x or something, and it's kind of a formula thing. I want to show you how it's derived because it isn't actually obvious. I don't expect you to derive this, but it's something I want you to look at, to think about. So let's find the volume of the shell. You have a height, right? We're going to have to multiply by height at some point. And that will be the difference in the function values. So if you have a bottom function and a lower function, that's what you'll get. So let me draw one more in here. So if you had something like this, so if that was y equals x squared, and then maybe the cube root, square root, square root of x, then we can revolve that little piece like that around the y-axis and creates that shell. Oops, it's not going to go down that low, is it? Okay. So the height will be that. That was the whole point of it. The height will end up being the difference of those function values. For that example, so for this example, it's basically this top one, which is here, but then you have 0, so it's a little easier. This one, you'd have a top and a bottom to find the height. Okay, that part will be easy to find h. Then what you have for these shells is you have a radius. You have an inside and outside radius. We'll call that R1. And then you have an inside radius like that. We'll call that R2. And so the thickness will be that difference. So we're going to let, sorry if that messes you up. I'm just trying to zoom in so you can see it better. We're going to let R1 be the outer radius. R2 inner radius, h, the altitude, delta r will be R1, the outside minus inside, R1 minus R2. That's considered the thickness of the shell. So it isn't really just your delta x because it's the radius of that whole thing. Now, let's look at this concept. The average radius of the shell is basically you add up the two shells and divide by 2. So you're doing the average of it. So R, we're going to say R, we're kind of defining what R is. R is 1/2 R1 plus R2. And then we're going to simplify this, and this is, I'm just kind of going for it here because I want you to see what's happening. That's going to be R1 plus R2. And then you'll see we're going to make a substitution later for when we see R1 plus R2. Okay, so keep that in mind. So the volume of the shell, V, is basically the difference of the whole cylinder minus the small cylinder, right? It's just outside minus inside. So the outside, so I'll just do volume outer cylinder minus volume inner cylinder. That's what you're actually doing. So volume of the outer cylinder, so that's going to be pi r squared h, right? Area of the circle and then times the height. So that's going to be pi r1 squared, that's outer, times h, minus pi r2 squared h. And then we're just going to factor out pi and write that as r1 squared minus r2 squared times h. Now, do you recognize how to factor this thing? Right, that's a difference of squares. So that's going to be pi times r1 plus r2, r1 minus r2 times h. Now, what is r1 plus r2? Ta-da! It is the average radius. Isn't that cool? Gotta love math. Okay, so this is so you're going to replace that. So let me just do a little highlight here. So you have this. I'm going to make the bigger font on that one, huh? Is 2r, right? They're the same. So do that substitution and you get 2 pi r h. And then what is r1 minus r2? R1 minus R2, I'm going to change that to my other font I like. This highlights the whole thing. R1 minus R2 is delta R. So we can call that delta R. Now that's looking more like a Riemann sum where R is the average radius. So what we have is that volume, so volume is equal to 2 pi times the average radius times the altitude times the thickness. Isn't that cool? Now we're going to have to do a Riemann sum and add that up, huh? So average radius basically is it's going to be a value, whatever value x that is. So when you come back here, we're just going to say it's right there, and that's just x. Or if you're going the other direction, the shell on its side, it'll just be y. So it's average radius. Altitude will be the function value and then delta x. Or you might have x and then the difference of an outside and inside might be altitude, and then that's delta x as well. Or you might have, or if you're going the other side, and there's going to be homework problems on it. I'm not going to ask you on it on a quiz or anything, but you could have a y in there, and then that'll be a delta y. So this is basically this direction. So if we do a shell on its side like that, that's what that one's about. Okay. So here's some derivation stuff again. So bear with me. Let W sub k be the midpoint. So remember how when you're in an interval and you say that arbitrary value in the interval is, the value in the interval is arbitrary. Well, if it's arbitrary, you can make it whatever you want, and it still works because it works for anything. So if we make it specific, that's okay. That's what we're doing here. Let W sub k be the midpoint of that. So you get volume of the shell is equal to 2 pi, and then that is your W sub k. And then it's f of W sub k, delta x sub k. That's what you need for this. Then you add those up. That's what you need for the Riemann sum. Okay, so now add up and take a limit. Right, so that's the next step that you would do. Take a limit as a norm of the partition approaches 0. I'm not going to define a partition and all that, but so volume of the solid, the whole thing, is going to be equal to, approximately the sum, because I'm not doing a limit yet, over all the k's of 2 pi W sub k, f of W sub k, delta x sub k. All right, so now take a limit as the norm of the partition approaches 0. And you get volume then is equal to the limit as the norm of the partition approaches 0. Sum over all the k's of 2 pi W sub k, f of W sub k, delta x sub k. All right, so that's a Riemann sum. So that translates to by definition, the integral from a to b. And I didn't, back here define the interval from a to b and all that. But then it's 2 pi, and then that's just x, f of x dx. Now that's the first case, right? That's just if you have an altitude. So that's like this one. So the height is just your f of x. But it could, if it's this case, then you have a top and a bottom. Okay? So, or, I just said or you can write volume as that difference. The square root from a to b of 2 pi x, and then f of x minus g of x dx. Okay, so that's your altitude. Okay. Next, we need to do examples. Let's see, I got 1, 2. So I got 2 examples. That'll be enough for another video. So we'll go ahead and stop this here, and we'll do examples next.